results about the large value set of the Gaussian free field. So let me give you that result, which sort of kicked off everything. So here's a theorem. Oh, this one is bad. So, a quick reminder, right? So we have H, in general, this is the discrete Gaussian free field in D, 0 boundary conditions, okay? And what I will look at, I'll look at a set gamma n, and then, Vn will be the box of size n in the square lattice. And where I put the box doesn't matter because I'm putting the boundary conditions, and the model is translation invariant. And so here's a theorem, which is essentially the work of Ding and Zaitouni. I think from 2011, and Jian Ding from 2011. Well, they in fact proved many other things, but let me. I think it's actually the bulk is from this paper. So I can, I'll tell you, I'll look at the set gamma n of T, which will be the set of points x in Vn, such that the Gaussian free field is larger than Mn minus T. And that's another omission that I made here. I should tell you what Mn is. So let me. So Mn was the scale, was the log and log-log term in the scale of the expected maximum. So this was the 2 root g log n minus 3/4 root g log n. Okay, so that was the sequence that Bramson and Zaitouni proved the maximum is tight around. Okay, and that will be sort of our running scale. It's the maximum, the expected maximum is this plus some constant. But we don't care about that constant that much, okay, in here. Okay, so I look at the set where my Gaussian free field is actually larger than this running scale minus a factor t. And now I'd like to, I'll tell you something about the structure of this set. So first thing is that there exists constant c and capital C, both positive, such that the probability that e to the ct is less than the size of gamma nt is less than e to the capital CT converges to 1 in the limit where you first take n to infinity and then t to infinity. Okay, and the second result is that there exists a constant c in infinity such that the probability that there exists 2 points x and y in gamma and and now the t will have the form little c of log r, okay, with the property that r is less than the Euclidean distance of x and y, and that's less than n over r. Okay, so then this converges to 0 in the limit n goes to infinity, r goes to infinity. Okay, so those are this is sort of extract statements of 2 theorems from these papers. Yes? Mm-hmm. Okay. Well, the method that they claim is new is the sprinkling method, which is really the consequence of, of the. Yeah, I guess it's the additivity of Gaussian processes in the end. Yeah. So, which is also true. Yeah. So so the point is that once you have, so essentially, once the tightness of the maximum around Mn is proved, you can kind of, bolster a lot of statements, and this is, one of the consequences of this bolstering. Okay. So essentially, the ideas are, things are proved in such a way that you sort of take, you decompose your Gaussian field into small part and large part. You'll see this appear again, and then you make an inductive assumption on the number of large vertices, and then the small part has to comply with that assumption, and that constrains certain events, and this is sort of how things are done. Okay? Because if you assume that there are too many high vertices, your small part would even bolster these further, and then and vice versa. So this is how these results are proved, essentially. Yeah. No. The limit is in the order written. First n goes to infinity, and then r goes to infinity. Yeah. The result is meaningless, when r goes to. Okay. Okay. So what's the qualitative picture you want to take in your mind from this? So if this is your box Vn, and I draw the set gamma n, what the first one says is that the size of the number of values which are just a notch below the maximum is only exponential in the difference. So it's finite uniformly in n. Okay, and in fact you have sort of an exponential estimate on the size, and the results of Ding in fact strengthen these constants, and one of these constants becomes essentially optimal in one of these results. But I'm not stating that. And the other result says is that if I look at any 2 points in the set, they're either within distance r or as far as n over r from each other. Okay? So this says that this set as a structure of a bunch of islands of size r, and well, where r is related to the cut of t through this relation, right? Through this log-log relation. And these islands are separated essentially by distance n from each other. Okay, so this is the structure of the set gamma nt. Okay, and that's I guess the most important message from this theorem for us. Okay. So I came back from MSRI and I started talking with Oren over, a lot of beer, and we actually very quickly came up with a consequence of this result that I will show you today, and and that led to developments that I'll comment on. There was sort of interesting timing of events that lead to the following theorem. Is that so? I'll actually. I did, yeah. He is keen on the spelling, yeah. Also pronunciation, but that is a different story. Okay, I guess I'll just hit you with the theorem then right away. I wrote it somewhere, but I remember the theorem. That's not the issue. The issue is whether I want to do it for. I'll do it for the square. Okay. Okay, but I actually have to do some introduction. So let me. Yeah. So let me actually pause before I state the theorem. I want to talk about the setup a little bit before that. So if I look at this structure, what this tells me is that I can now I have a uniform control on the size and the values of this set. So I claim that this immediately has a corollary. Is that if I look at the ordinary extreme value process associated with these Gaussian values, then this process has a limit. Okay, sorry, it's tight. Okay, so if I look at a random measure eta, which is the measure. So let eta n be this, I enumerate all points in Vn. And I take the measure, which will have two components. So it will be a product of the delta mass at x over n. So I take the x coordinate of the point and scale it by n. And then I take the value of the field at that point, and I reduce it by mn. Okay. The claim is then the family of processes is tight. Okay, so what are these processes? So these processes are point measures. I'm supposed to evaluate these point measures with respect to functions, continuous functions, which are bounded and have compact support. Okay, and so the natural underlying space of this is a measure on the unit square across the real line. Okay, so this is not a compact space, but if I take a set with compact support, it's contained in the unit square cross an interval. Okay. What? Well, it can be. I will need to make it closed first because of tightness issues. If I want to talk about tightness, I don't want the mass. I don't want the points run off to the boundary. It's certainly a measure on that space. Okay. At this point. So if I take any function with compact support, its support is contained in the unit square, closed unit square cross an interval, and the number of points that this will evaluate to non-zero in this set is finite with probability 1 by this theorem. Okay? So the total mass of this process cannot blow up. What? It could be next door. Somebody's phone is ringing, but it's fine. I'm not disturbed by this as much as by Anton. Okay. So all right. So this sequence of processes is tight, and since the underlying space is separable, the set of those continuous functions is separable. So I can extract converging subsequences, because I'm supposed to test these processes by integrating against those functions. Okay? So which means that the idea is to extract a converging subsequence and characterize its law directly. Okay, so that's sort of the idea that naturally springs to mind whenever we have tightness. And this is a program I'll execute for you. Okay, so let me in fact give you the theorem, but I'll actually give it on the other board. Okay, so here's the theorem that comes out of this. Actually, I still have to make some stopover. Okay, so there is a little problem. Okay, and the problem comes from the fact is that these, although small, those are not single point sets. Okay, so if you and on the other hand, and when you scale everything by n, all of these islands will contract to a point. So every limit that comes out of this process will have the property that there'll be sort of fibers. Okay, and on these fibers you will have a maximal point, but then you have more and more points running down. Okay, so every limit that you obtain from this, so let me draw. This is your square. This is the real line. Will have the property that there'll be, points which will look like this. There'll be a maximal point, and then a family of points going down like that. Okay, and in fact there'll be more and more points on that fiber as you go because of this sort of exponential growth of the set. Okay, so this is not anything that would naturally be be describable by some anticipating Poisson laws, really, because that's what I had in mind when I saw this first. And so what happens is that you have to first prune your set of points a little bit. Okay, you don't want to take all points in the cluster. In this cluster, you want to take just one representative point. And the most natural thing is to take the maximal point. Okay, just to take the local maximum. So instead of this, I define a measure which is sort of a reduced version of this measure, where I take the same sum, but I only take the point x if it's equal to the maximum over an R neighborhood of the point at x. Okay, and this is my basic object, and the lambda r of x is the set of points in Z2 such that the distance is less than r. Okay, So these are, you know, what we would call our local maximum, because the point x only gets counted in this if the value dominates in our neighborhood of the point. And, you know, the natural thing is, of course, you know, we have that r already built into that picture, right? Because, you know, if I do the cut of r, then the islands are of size r. And then there's a, you know, with probability 1, there's a unique point which dominates all of the values. Okay? All right, so here's the theorem finally. So let's see if I can fix Oren's name in here. So, the theorem is that let Rn go to infinity such that n over Rn to infinity. Okay. Then eta n Rn converges in law as n tends to infinity to a Poisson point process with intensity z dx e to the alpha h dh. So, you know, so it's a Poisson process on two, you know, on two variable points indexed by two different commodities. One is a point in a square, and the other one is a value in R. And the intensity measure takes a product form in this case. That's the statement. Okay, where, okay, z dx is a random Borel measure on the unit square, such that z a is equal such that for every a you know, Borel set on the unit square with the Lebesgue measure of a is 0 implies z of a is 0 almost surely. So this is 1, 2, z of the whole unit square is finite almost surely. Okay, and alpha is 2 over root 2 over g, which is root 2 pi. And there's minus, yes. Okay. Push this further up. Okay, so that's the statement. You know, there are a few other things we can say about this measure, but I didn't try to push everything in here. So first thing is that whenever you take a set of 0 Lebesgue measure with probability 1, z evaluates to 0 on this measure, but of course you have uncountably many of such sets, so it's not true for all of them at the same time. But it's true for the boundary because the square has a U0 boundary. So this measure puts all of the mass inside the set, okay? And it has only a finite mass, which means that this is a locally finite process. Okay. Right. So Z has. No atoms almost surely. Okay. So conjecturally, I don't think that this has been proved in any of the instances, even, you know, not completely related to this, is that this measure, in fact, is supposed to be concentrated on a set of 0 Hausdorff dimension, okay? So it's almost atomic, but not quite, okay? Yes? Yeah. No. So it says that if you fixed a set of Lebesgue, a Borel set of 0 Lebesgue measure with probability 1, z will evaluate to 0 on it. Yeah. It is at the end. Yeah. Whereas, of course, you know, you cannot do this for all null sets because there are uncountably many. Okay, you cannot have the almost. No. This is real. It's real. It's, you know, that's what I said. It's this measure is concentrated on a set of 0 Hausdorff dimension. Okay, so obviously it will not, right? Okay. So it's a very sparsely concentrated measure, but the support is so the support moves around so much with the randomness that any Lebesgue null set will receive zero mass. Okay.
There are some out-of spaces that you use functions to define them, like instead of using x in the power of t, you use log x or something like that. Can you find the dimension in this sense?
No, I cannot even prove the dimension in the ordinary sense. Okay, this is a conjecture, which is not known. Okay. Now, since Anton forced me to do this, I will again, I'll add more statements in here. Okay. I wanted to talk about these things later, but let me just add another clause in here. And 4 is that for every A Borel with a positive Lebesgue measure, Z of A is positive almost surely. And okay, so once we start talking about the detailed properties of this measure, then this measure puts zero mass on every null set, but on every set of positive measure, it puts a positive mass almost sure. Okay. So which means that that's a consequence of the fact that there'll be no region in the set A of positive Lebesgue measure which will not receive any points of the Lebesgue process. Okay. Okay. Now it becomes ugly because I have a long list, laundry list of properties. Okay. So what I'd like to explain to you today why this structure appears. I will not be able to give you a proof of all of these properties. These are, proofed in the statement. In fact, what I will show you is that every subsequential limit of this family has this form, and then I'll refer to a theorem to tell you why the limit is unique. Okay, the measure Z is unique, and it's independent of the Rn sequence, and of course, the convergence take place makes it unique. Okay, so what's the property that characterizes distributional? Invariant. Okay, so I want to tell you. So this is in fact what started the whole game. So I claim the following. So I have already argued that the process eta n is tight, and of course, since this being a pruning of this process. Then eta n r is also tight. Okay, so here's a proposition. I need to get a better chalk. The proposition says is that let eta be a subsequential limit of the processes eta n and Rn. Okay, so I'll just think of fixing the Rn to a sequence of this form. So Rn grows to infinity, but not as fast as linear. And let me extract. I know that this family is tight, so I extract a converging subsequence. Okay, then the following is true. Then for every f, which is from, okay, I'm writing it from the square. To positive reals with continuous compact support. Okay, so those are the functions that I'm allowed to test my eta process on. I'm going to use a notation, which I'll write down if you want me to. So eta is a measure, f is a function, so I denote the integral of f with respect to eta by this inner product notation. Okay? So the statement is that this is equal to the eta ft for every t positive, where f ft of x and h, so these are functions of two variables on the position, and r is minus the logarithm of the expectation started from 0 of e to the minus f of x, and then I write h plus bt minus alpha over 2t. Okay, with bt is a standard Brownian motion. And of course, alpha is this 2 over root g. Sorry, I'm actually writing this wrong. 2 over root g. And I miswrote it here because I repeated this so many times that I made a mistake. Okay, so that's the statement. Okay, I'll let you stare at this. So do I have to write this? This is the integral of the function f against the eta process, and as long as the function is positive, I can integrate it. It could come up to be infinity. Well, e to the minus infinity is 0, and you know ft. So ft is a function where I take the I can write this in the form of e to the minus ft is equal expectation of e to the minus f with respect to this. And what I do is that I do nothing in the first coordinate. In the second coordinate, I add this drifted Brownian motion. And I take expectation of that at t. Okay? So this is, in fact, sort of an evolution of e to the minus f by the semigroup of this process. And naturally, because bt is, can take any value with positive probability, this is no longer compactly supported. But the decay to infinity is exponentially fast. In fact, exponential and quadratic of the argument. Okay, so this is still and by the fact that this is non-negative, this is less than 1 with a minus sign. This is non-negative function too. So I'm allowed to write all of these formulas. Okay, so this is a statement, and you say, what on earth does that mean? So let me give you an explanation what that means in more layman terms. There's a reason why I write it like this, because it avoids certain tightness issues that I have to deal with if I start to write this at the level of the point processes. Okay. Actually, I can just take this whole thing away. This is a good system, I agree. Well, the problem is that we don't have water access there. So Christoph Thiele used to, when he was at UCLA, he had his own private bucket, which he would take into the classroom. I might. Well, currently, yes, yeah, but not so much that we would not erase the boards with. Okay, so let me try to explain the proposition explained. Okay, so let me try to write the following. So I have the eta process, and I'm assuming that I know that the process is it's a result of a limit of a tight family of processes. So it puts a finite number of points into any compact set. So I can in fact enumerate the points. Okay, so I can write this in the form xi hi. Okay. Now let me do the following. Let the B, T, I be IID standard Brownian motions. Okay, let me do that. And now let me simply add the corresponding diffusion generated by the standard Brownian motion to the h coordinate of the ith point. So let's define eta t to be the measure okay, so it's now a point mass at this point. Now, I can certainly, enumerate such points. I can define this for every t. Of course, what I'm no longer guaranteed that this is a well-defined point measure. I mean, point measure in the sense of a radon measure, evaluating to a finite value almost surely on every compact set. Okay. Now, you can in fact use the theorem which I just erased to argue that it is, because we know that the number of points with h values from larger than minus some large capital K is only exponential in K, okay? Because I showed you that the size of the gamma set grows exponentially. Now, if you want to bring that point using that Brownian motion to that level, that Brownian motion has to have an exceedance which is of size K as well, at least, because in fact this drift guy even pushes it down, okay? Well, that costs you e to the minus K squared. So you have exponentially many points, but with probability e to the K points, but e to the minus K squared, it costs you to bring that point up. Well, by Borel-Cantelli argument, you will find out that you're not going to do it more than find a number of times, okay? So this is essentially would be an argument which would prove that this is in fact a well-defined object, okay? Almost surely for every t, all right? And so now let's look at this a to t, and let's integrate. Now let's pick f from the unit square cross R compact support, continuous, of course. And let's integrate, a to t against this f. Well, I claim that because of this property, okay, this becomes the integral of d eta. Eta, I should write it as a measure, eta dx dh of f. Actually, I want to write it already in the exponential language rather than that. So let me erase this. Right. So let me write the expectation of minus eta tf, and let me take the expectation with respect to the Brownian motions. Okay, so I will, my eta is fixed, so let me sort of remember that eta is fixed in this game, okay? Then, of course, this can be written, as a sum, and the sum can be written as a product, and the exponential of that can be written as a product. And since the Brownian motions are independent, the expectations of each Brownian, of each term is just handled by expectation of one Brownian motion. So you get a product of the terms where the Brownian motion happens, and then, when the dust settles, you'll find out that this is exactly e to the minus eta times the function ft, which I defined above, because e to the minus ft is exactly that, okay? If e to the minus ft xh is defined as the expectation of e to the minus f of x h plus bt minus alpha over 2. And that's exactly the definition that I have above. Okay, so this is how I rewrite this. And so if I now take expectation of this with respect to eta, I get the expectation of the random eta process evolved using this evolution, and that's equal to that. So proposition implies that the expectation now not constrained, right, to eta f is equal to the expectation of e to the minus eta f for every f as above. Okay, but this is exactly what characterizes equality in distribution for the point process. Okay, so the statement of proposition is sort of a dual version of a statement of equality in distribution for the limiting point process. So what I'm claiming is that the limit point process, any subsequential limit process, will have the property that if I take its points and evolve the second coordinate using these independent drifted Brownian motions, then distributionally I get the same thing at every t. Okay, for every t, not as a trajectory, of course, but at every time slice I'll get distribution of the same thing. Okay, so this is how we will actually prove the proposition. Okay, how it was discovered, and this is how you prove it. Now you have to write it in this dual language because that that avoids the discussion of the tightness issues. But I'll avoid that here as well. I'm sorry? Yeah. No, but for this explanation. But when you're proving this, yeah, somewhere you have to do the work. So. Yeah, no. I'm not talking about tightness of the process. I'm talking about the fact that the time evolution does not produce immediately blowups. Okay. When I compose the points of the limit process with these boundary motions, blowups can result. Points can arrive from -infinity to the compact interval around 0, and then I have to worry about that. Okay, but I will not worry about that anymore. I kind of explained to you how it's handled. Okay, so how is the proof idea of proposition? Because so far I only explained to you how to read the proposition in probabilistic terms. Okay, so what you do is that you write. So we use the Gaussian decomposition. Okay, so I take the Gaussian free field, I scale it down a little bit, and that gives me a room that if I add another copy of a Gaussian free field with correct covariance, I get the original thing back. Okay, so if H prime and H double prime are equal in law to H, and H prime are independent of H double prime. I think that Anton already got used to this symbol. So did everybody else. It may be, yeah. I don't think I knew it before I... What? Oh yeah, I haven't learned that skill yet. I think that's high school. You have to go to high school in America to do this. Okay, so I claim that then H is in law equal to 1 minus S to 1/2 H prime plus the square root of S H double prime for every S positive. Actually less than 1, of course. Okay. So this is just a statement about the covariance structure. Okay. So I pick a particular S, and there will be such that this random variable will have a unit. I mean, this is a random field, so the random field will have a unit covariance. Okay. So I pick S to be T over, and the covariance of this is to the leading order G log n. So I'm going to write this S to be T over G log n. And I say unit. Well, no, it will not be unit. It will be T. Okay. Okay. Okay, so then I have that H equals, so let me write this again, 1 minus T over G log n to 1/2 H prime plus square root of T over G log n H double prime. Okay, and now, I write this in law, but what I can do is that I can take 2 copies of a Gaussian free field, add them up in this form, and then proclaim the results to be my final Gaussian free field. Okay, so I will now, from now on, I'll treat this equality as equality coordinate, pointwise rather than its distribution. Okay, all right, and now I would like to study the extreme points. So I look at, so the idea is that this is a small guy, this is the small perturbation of that. So I pick a point X, which is a local maximum of H prime. Okay. Well, we know, and the local maximum is close to Mn. Well, if it's close to Mn, then this is a large value, okay? And the value is, in fact, of the order of the order log n. So it makes sense to start Taylor expanding in this expression because, when I expand the first order term, then, I get, as a 0 order, I get 1. The second order, I get something over log n, but that will just exactly cancel the size of that point. And the next order term will already be small. Okay, so by Taylor, okay, and let's just assume that H prime of X is larger than Mn minus T. Okay, let me just assume this. So let me in fact look at a specific point X. Okay. So, let me, I'll write this. So pick X such that h prime x is larger than mn minus t. And remember that mn is 2 over root g log n times quantities 1 plus O of 1. Okay, so the leading order is 2 over g log n. Okay, and then I expand, so then hx is 1 minus this, so it gives me 1 minus t over 2 g log n times h prime of x plus t over g log n h double prime of x. Okay. However, there's of course further order terms, but the next order term is this quantity squared, and because this is also at most of order log n, because the maximum is ordered, then I can just hide this into a little O1. Okay, we know that the largest value the free field will take is of order log n. So. No, this term is unit variance. This is there's a square root. Yeah. This term, just think of this. This is really, if you look at any point, this becomes a normal random variable with mean 0 and variance t. Okay, so this is of order unity. So I will only, I'll really drop everything which is vanishing order. Okay, so that's the second order term from here. And now since h prime of x is of order mn, so I can replace h prime of x by mn and again lose something which is vanishing order. So I can write this as, okay, so first thing I keep the h prime of x for the 1, and then in here I replace this by t over 2g log n times mn plus square root of t g log n h double prime of x plus a little o of 1. Again, I drop the term t, which is t over log n, which is of vanishing order. So far, all of these are of order 1 over log n. Okay, I'll now erase the statement. And okay, and so now I'm ready to wrap up. So, but mn, as I said, again, up to quantities of log n over log n correction is essentially 2 over root g log n. So I can replace that further. Replace that further by, by the leading order. So I claim that that's equal. So hx is that equal hx prime minus, right? So this is 2 over root g log n. The log n's cancel, the 2's cancel, and one of the root g's cancel. Right. So I get minus t over root g. And here I get plus root t, and let me write this like this: h double prime of x over square root of g log n plus little of 1. Okay. This is how I write it. Okay, so you see that the shift in the variance resulted in a deterministic downward drop of the value of the field. Okay. At those maximum values. So now let's examine what this field does in the neighborhood of such points. So I know that if I have a value of h prime where the value of h prime is large, the neighborhood of that point where this applies is very small. It's of bounded order. Okay? So I really need to only examine the behavior of the h prime field on that region. Now the h prime field is a Gaussian free field, which at short distances is heavily correlated. Okay, the expected difference of hx minus h neighbor of x squared has a bounded variance. Okay, so of course the field is not going to make big jumps. It's going to vary by quantities of order unity, and then of course those variations will die once I divide by log n. Okay, so on each of these islands of the h prime field, I can regard the h double prime field scaled by this as a single random variable, as constant. Okay? On the other hand, if I take two different islands of the h prime field, that's where the picture of the separation, these are distance n from each other. Okay? Now the H double prime field, the correlation at that distance is already of order unity. If you divide it by log n, it becomes of a vanishing order. So the double prime field, scaled by the root of log n, essentially acts as a single random, as a constant on each of the islands, and these constants are almost uncorrelated island to island. So they behave as independent random variables. Okay, so that's sort of the argument vaguely. So by the island structure of the gamma n T set, we can regard as the H double prime of x over g log n as constant on each island and uncorrelated between islands. Okay, and you can do this quantitatively, and if you look at sort of the proof, that's what you have to do. Okay, you have to do some little coupling arguments to kind of get rid of this residual dependence that you have between the islands. Okay, and once you realize that, then then this acts as a standard normal shift in each of the values, and if you scale it by t, it looks like the value of an independent Brownian motion evaluated at time t. Okay, so this is how you put things together. And then, so this tells you that if I look at the local maximum of this field, then the distribution, it becomes a local maximum of that field, shifted by t over root g, and with added independent copy of the Brownian motion. And that's exactly sort of this ideology that enters in here. Okay, so this is roughly the idea that goes in there. If you want to write it up, you have to do sort of lots of conditioning and treatment, and it takes 3 pages to write, in fact. Okay. Write this at the level of the point processes. Okay, so regard t root t times the h double prime of x as Brownian motion at time t associated with the island of the H prime field. Okay, so I know that this is kind of verbose, but I don't want to go through the formal proof. The formal proof is written, and you're more than welcome to have a look at this. Okay. Sorry, let me get the board. It has right. It only uses the core structure, which exactly. Yeah. It's totally abstract. Yeah. Yeah. You will see that this whole process, the whole proof is sort of a tour de abstract, okay? It's sort of a sequence of abstract nonsenses put together that, well, that's what mathematics is about, right? So, but Anton is absolutely right. Every time you have this decomposition and you have sort of the reasonable decay of correlations, then you can do this game, okay? The question is, what do you do with this information? All right, and this was actually done in 2012 in June, but then there was a summer, and Oren needed a job to get a job in the fall, and so basically this project was put on hold because we didn't have a good idea how to proceed, and we had to finish other work that was done. And so that took 6 months. And then, I'm about to sit down for Christmas dinner with my family at 2012. We celebrate Christmas on Christmas Eve, actually. This is a Czech tradition. And I receive a phone call from an Israeli phone number. So, it's Oren, and says that he has a Christmas present for me. And I say, okay, it's very nice. So what is it? And he said, well, guess who we should have asked how to solve this problem. We were kind of, slowly working on the problem whenever we had time, but we had no idea. And it turns out that we should have asked the very Tom Liggett, who is a colleague of ours at UCLA. But of course, since we never really talked about the project, during the work time, it never occurred to us to mention this to him, okay? So it turns out that Tom Liggett studied a related question that helps you solve this problem. Okay, to push further the information about. That is correct. It took us about a week to realize that you have this distributional property, but for 6 months we had no idea what to do with it. Well, we had a PDE-based proof, so you can write this thing, in terms of intensities associated with this limit process. You can write a sequence of PDEs. You solve these PDEs. They give you the information that the theorem says. However, then you find out that all of these intensities are infinite, okay? Because it's a feature of the process that if I take the expected number of extreme points in a set, it sort of blows up logarithmically, okay? And so there is no limit, and therefore this whole approach was out of the window. And we didn't know how to really approach this otherwise. So we didn't know indeed. Yeah, but that's very nice, but I never worked in spin classes. So yeah, well, I worked in different fields, so I think that's totally acceptable. Okay, so what I'd like to, so what Tom Liggett has worked on, so he, all of his life, he worked essentially in particle systems, and the question that he tried to address was that consider a particle system on a general space. Okay, so a particle is a point. So a particle system is described by a random point measure. And he wants these particles to evolve using independent Markov chains. So the idea is that you take a point measure, which assigns almost surely a finite value to every compact set, and then with each of the sample points of the measure, you associate an independent Markov chain that starts from that, and then you just evolve the measure using that. Okay, very similarly to what we do. And then what Tom did is he characterized the invariant measures for such process, and he in fact showed that under reasonable conditions these become these are Poisson with respect to the random intensity measures, so they are Cox processes. And in fact, he gave also conditions on which characterize the intensity measure using the ordinary Markov chain. Okay, and so that's what I'd like to give you. I've already spent a lot of time on deriving this. Okay, so here's the theorem. Okay, so let me do a little bit of setting. So this is Tom Liggett's 1977 paper. So despite what Anton says, this paper is actually not so well known. Right, that is true, and it has only 10 citations. I guess that may increase now. Okay. Okay, so here's the general setting is that if you take a locally compact separable metric space, and the P is a Markov kernel on X. So that's so it's so Markov kernel is an object which takes a point and outputs a measure, right? So it's it's an object of this form. So it's a point indexed measure, probability measure, and you can define the process. So given a measure, given a point process, a point measure, eta on X. So if a point measure is a collection of points, you can write the eta as the sum over I delta I. Okay, I'm sort of indexing it by the naturals because all of my measures will have infinitely many points, and then you define eta n to be the measure where you write delta x I of n, where xn I is the sample of the Markov chain, as the law of the Markov chain started from AI. Okay, so that's that's the structure you would like to have. Okay. Now you might okay. So let me show you that this is essentially what we had before. Is that if I now take f, a function which is continuous with compact support, then if I take if my eta is fixed, so I condition on eta if you wish, or not considered random, And if I integrate my eta n against f, then I claim that this becomes, well, by the property. So you fix the eta, right? So you have independent Markov chains. This becomes a product. The product you can exponentiate. So this becomes e to the minus eta f n, where fn of x is the minus log of Pn of e to the minus f evaluated at x. Okay, so P to the n is the nth convolution of this Markov kernel, the product of the kernel, and you apply it to the function of e to the minus f. I should write the function to be positive, so that I don't get into issues with integrability in here. Okay, so this is the relation that we saw in the specific case of my diffusion. And then you can, I will not write this, but then you can argue that if your Markov chain is sort of so reasonable that if you start in a compact set, you're not immediately going to leave a large compact set which contains it with uniformly positive probability, then this is well defined for all n. Okay, so you need some small structural conditions on that, which I'm not going to write. Okay, and here is the theorem. Okay, so if the following, so there's a condition which I call uniform dispersibility condition, and this is the statement is if for every C compact, the supremum over all x in x, the Pn of xc goes to 0 as n tends to infinity. So this is a condition which says that no matter how far you start, wherever you start, the probability that after n steps you will be in a compact set goes to 0 uniformly in the starting point. Okay, so this rules out all of the positively recurrent Markov chains, for instance. Okay, because a positively recurrent Markov chain will keep returning to a compact set uniformly. So the chain needs to be dispersive. So Brownian motion has this property. Okay, so it sort of spreads, but it keeps returning, say, on the real line, but the probability that you will be in an interval of length n will go like 1 over n to, in an interval of a bounded length will go like 1 over n to 0, regardless of where you start. Okay, so this is a reasonable condition to assume. Then every invariant measure for the chain. Okay, so I have a Markov chain that starts with eta and moves around to gives you a sequence of random measures out of this. Has the form. It's a Poisson point process with some random intensity measure, where m is a random Borel measure on x, such that, okay, so one thing is that it assigns compact sets a finite value almost surely. And two, m composed with p has the same law as m. So if you take this measure and you formally integrate the px dy against over x, then what you get is a new measure. The new measure is random, but its law is the same as the law of m. Okay, I actually had I had plans to prove this for you, but since I guess I'm out of time, well, I will still go on for a little bit because I want to at least wrap up the theorem. But I can't prove this for you in the time that I don't have. So there are two aspects to this. You have to sort of employ this non-dispersivity condition, and that's essentially what's responsible for Poissonization. And then you have to, in fact, construct the measure m. And that's done by compactness arguments and subsequential limits. Okay? So the proof is essentially written in our paper with Oren, but it, you can also consult the original reference. So Tom refers to this as a folk theorem, which is funny. So it was probably kind of guessed or surmised before, but never was written down. Okay. Now this is not the end of the story, because what you need, and that's in fact really the substance of the Liggett paper, is that you need some way to use the condition that the MP is in distribution equal to M. Okay? And that's not automatic. In fact, what you would like to do is that you would like to see that that implies something that's quantifiable just in terms of the Markov chain itself. Okay? So here's another theorem. So this theorem itself would not be very useful because this is not enough information to work with. Okay? But Tom Liggett fortunately proved another theorem. So this is again. Okay? That the relation MP in law implies MP is equal to M almost surely if P is a aperiodic Harris recurrent Markov chain, or 2, P is a random walk on non-compact abelian group without proper closed invariant subgroups. Okay. So there are other statements in the paper which extend this to some transient Markov chains. So for transient Markov chains, you generally don't expect this, and there are some counterexamples. The aperiodicity is also required. You can provide these counterexamples with aperiodicity. What's really good is that it works for all random walks under this general condition. Okay, and the proofs use non-trivial facts from sort of Choquet-Denis theory. Okay, so this is in fact a pretty pretty technical argument. Now, what do we in our case we do not have a recurrent Markov chain because our Brownian motion has a drift. Okay, and so that takes the condition 1 out, but I still state it for your interest. Now, but we do have an additive process, and so we have a random walk. So in our case, the Markov chain is the Brownian motion with a drift, and in this case, the second condition applies because the Brownian motion explores the whole line. There is no invariant subgroup of the real line. Okay, so so now why is this good? Well, this is good because what it says, that if you know MP is in law equal to M, then what it tells you that MP is equal to M in almost surely, which means that up to, on the set of measure 1, M is in fact an invariant measure for the Markov chain. So all that you need to do is to classify all invariant measures for your Markov chain. Okay? So what is left to do, classify all invariant measures for the Markov chain. Okay. All right, so there's a little caveat in here, is that's because our Markov chain is actually not exactly just Brownian motion with a drift. We have really a two-valued space. We have an x and h coordinate. The Markov chain does nothing with x. It just keeps it constant. And it only moves the h coordinate, okay? So what you have to do is that, so we first use this theorem to write the limit, proof of the, BL theorem. I just give you a sketch, of course, on the basis of this, okay? So, by the Liggett 1 theorem, we know that, so we pick eta to be the subsequential limit of these eta processes. And by the Liggett 1 theorem is we know that eta has the form of a Poisson point process on the two coordinates, okay? That we have in general, because there was no specific condition that one had to deal with. Okay, so this measure has this form. Now, what I will do, so the trouble is that the process does not really do anything with the second coordinate. So what I do is that I introduce, I integrate the first coordinate, right? So I introduce a measure on h, which is the measure on, on rectangles. So I just take a rectangle, A being a subset of a square, being a Borel subset of the real line, and I define an A-index measure in B, okay? And now, since the Markov chain operates on the second coordinate, that if my QT if my QT of F, let me write it like this, QT of H B is the probability that the Brownian motion, so H plus BT minus alpha over 2 is in B. So this is the Markov kernel associated with the process. Okay. Then by the properties of Liggett theorem, I know that LA QT is in distribution equal to LA for every t larger than 0. Okay, so that's the consequence of using Liggett theorem 1. Okay, so what it says is that this is a random measure which is invariant in distribution under the composition with a QT kernel. Okay, now I use Liggett theorem number 2 because this is now the honest random walk on a non-abelian, non-compact abelian group. And so I only need to classify invariant measures. And for that, you can pull another abstract theorem, which says that if I take a random walk on R, that all invariant measures have the form of an exponential, random walk on R with these properties, with the no invariant subgroup property, that all of the invariant measures take the form of exponential times the Lebesgue measure. Okay, so all QT invariant measures have the form e to the bh dh for some b. Okay. Right. So, right. Okay. Well, there are, the point is that there are still more than one. Okay. The invariant measures for this drifted Brownian motion. So you check, now the specific condition, and you find out that there are two values of beta which is admissible. One is the Lebesgue measure, where beta equals 0, and one is the measure with beta equals alpha. Okay. So in our case, the beta equals 0 or beta equal alpha apply. So our specific case, beta can be 0 and alpha allowed, only allowed. Okay? So this tells me that my measure, that my LA has the form which I will write as, LA dH, has the form of z of a e to the alpha h e to the, sorry, I guess minus alpha in this notation in here, okay? dh plus z tilde a of times dh, okay? So my measure has to be a combination of two measures like this, okay? Where these are, random because they share the randomness of this, okay? All right. But I claim that z tilde of a has to be 0 almost surely, because if it weren't, then the Poisson point process associated with this LA would have points spread all the way up to plus infinity, okay? Because that, you would simply take the composition of a Poisson point process. And we know that this is not true because the maximum of the distribution is tight. Maximum of hx minus an is bounded. Okay, bounded in distribution. And so this means that LA of dh takes the form z of a e to the minus alpha h dh. Okay, and this is true almost surely. Which may depend on A, of course, because, I have now made an equality which, where A was fixed. And now I use the fact that there's a countable basis to the sigma algebra to, find a unique null set for which this will be true on a generating class of sets. And then the fact that this is a measure then implies that this is a measure, and I can therefore extract an honest measure on the square from these objects. Okay, so there's a little caveat of this. So this means that m dx dh is equal to z of dx e to the minus alpha h dh. And this is how you get the structure of the limiting process. Okay. Now let me, because I want to somehow wrap this up at least. So let me say, one more thing. I learned from Gero yesterday that if you have given 75 minutes and you lecture 90, then some people still stay. Yeah, I know. Okay. Now I just want to give you an idea, because what have we accomplished so far? I have extracted a subsequential limit. I showed you that it's associated with a unique, with a measure z, such that it's a Poisson point process with respect to this intensity measure, where you have a z measure of this form. I have not proved all of the properties of the z measure, but it's not important. So the question is, how do I actually, now get rid of the subsequentiality? So in fact, this theorem we had in around, just after the Christmas of 2012, and then I went to Stanford, and then I gave a talk on this. And then, Amir Dembo was saying, oh, this is strange, I think that Jian Ding and company are working on something related. And lo and behold, in 2 weeks we get a paper from, the Bramson, Ding, and Zaitouni team. So this is 13, which says that the maximum converges in distribution. Okay, I've already shown you that this is in fact a tight family of random variables, so subsequential limits are possible. Well, what they proved is that the limit in fact exists. Okay, and that was absolutely perfect for us, because this was the thing that we didn't know how to overcome. We could now use this technique to in fact prove the uniqueness of the limit. Okay. And the way the proof works, so okay, again, so we in fact had to, understand this paper pretty well, but I'll give you an argument which only uses this theorem and proves to you that the total mass of the z measure is in fact uniquely distributed. Okay, so the Poisson point process convergence essentially implies, you have to do some, limit arguments, essentially implies that if I look at the probability of the maximum of hx minus mn to be larger than t, then this converges to the expectation of e to the minus 1 over alpha e to the minus alpha t, the z measure of the whole square. Okay, so that's basically by, maximum is not a continuous function, but you can approximate maximum by continuous functions to make this happen. Okay, so we see that the maximum, the limit law of the maximum is, essentially the Laplace transform of the total mass of the measure. Okay, so this was, so this was true for our, for our subsequence. So when we had a subsequential limits only, we had this for our subsequence. But what this gentleman tells us is that the limit of this is independent of the subsequence, which means that this quantity is independent of the subsequence, which means that the Laplace transform of any z measure I can obtain is the same of this total mass. But that determines the law of z uniquely. Okay? So existence, let me write this and then I pay attention, okay? Implies that the law of z of 0, 1 square is unique. Okay? So Anton was saying. Right, so it is true, but it actually, if you want to really write the full proof, you have to really open the guts of their paper and in fact prove more than they proved. Which was unpleasant, but we survived that ordeal. This is one of the hardest papers I've actually had to deal with, because they somehow rushed to get it done, being alerted, and somehow I feel, I'll say it in public, I think there's still a feeling that, we are in competition. No, we are in collaboration here, because what happens is that they provided something we could not do, and we provided something they could not do. So nowadays, this statement actually appears in their new version of their paper, but they did not have that statement back then, at least not in the version they sent us. Okay, and the proof hinges on understanding this Laplace transform connection, and the Laplace transform connection is only enabled once you have the Poisson structure of the limiting process. Okay, so this completes the lecture. I apologize for going over time, but I've said what I intended to say. And tomorrow I'll try to tell you a little bit more about how you can push this further. So there are two directions. One, you can use conformal invariance, or you can sort of look into local behavior, what happens when you're not only looking at the local extrema, but you're also looking at points around. I'll decide, based on how I feel, what I can manage in the 75 to 90 minutes you give me. All right, thank you very much. Depending on who you are, yeah. Mm-hmm. Right, so you start with, I guess I erased all of this, right? So you may start with the deterministic measure, point measure, but once you apply one step of random Markov chain, so you get a random measure. Okay, so it's like for the Markov chain, you start with a point, but the value of the next step in the Markov chain is already random. So it gives you a trajectory in the space of these point measures, and you can ask yourself a question: what's an invariant measure on these measures? You give me a law on these measures, which is invariant under this evolution. So that will be an invariant measure of this measure-valued Markov chain. Oh, why it is random? You mean? Well, that's what comes out. There's nothing you can do about it, because, for instance, you could sample your original measure already from that. If you have more than just one invariant measure for the Markov chain, you can consider a convex combination of these laws, and in fact, a random convex combination. And that will perpetuate in the, so this is a homework you can check, is that if you start with a Poisson point process with respect to any random measure on the invariant measures of the Markov chain, it will be invariant for this measure valued Markov chain, okay? So when you're approaching from outside, when you want to characterize all measures, this is what you end up having, okay? Now, the trouble is is that you get only that the measure from the derivation, you get that the measure is invariant in distribution. And you would like to, so in general, for the general setting, you get the MP is equal in law to M. And that doesn't mean that M is an invariant measure itself, or a convex combination thereof. So extra conditions are needed, and that's the second Liggett theorem, which says that under these conditions, you in fact have a random convex combination of invariant measures. And that's, again, the best you can do, because you could already start with that to begin with. Okay? That is true, but I think that the same theorem would apply to 3 and higher dimensions, in which case M is actually a Lebesgue measure. Right, right, but there are examples, right? So this theorem, with different scalings, the characterization of the limit, if you look at the extreme values of a 3-dimensional Gaussian free field, okay, it will also have the structure, the limit structure, but in this case, the Z measure will in fact be just the Lebesgue measure, okay, because there the maxima really appear as honest Poisson point process with uniform intensity, okay? Whereas in this discrete Gaussian free field case in 2 dimensions, the correlations remain present in the limit, and they are now hidden inside the Z measure. Okay? Yeah, because you try to characterize all possible measures, and and those are in there as well. Okay. So I've spent, so the point is that I believe that, Anton is absolutely right. And in fact, I spent about a month trying to bypass the use of their theorem. Not only because, they didn't have it ready for us at the time when I needed it, which was January 2013. It only came up in February. So that was the month when I was trying to sort of, prove the uniqueness directly. And you can prove a lot of properties of the Z measures. There's the reflection of the Gibbs Markov property. With fingers crossed, I was hoping to in fact prove conformal invariance, which is now established in another paper with Oren. If you put all of these together, you could hope to sort of work with the continuum object directly and use maybe SLE techniques or whatnot to prove to characterize the limit laws directly. Okay. However, I was not able to do that anyway. Anyway, there is an overall constant that these invariances would never give you. Right? Because all of these distributional identities would identify the law up to overall constant. Because typically, you say the law of this is equal to the law of that, so a constant multiple of this would not do anything. Okay. So some work is needed in there, and that's sort of unpleasant. But maybe we can overcome this by just rewriting their proof.